Hey, Calc students, this is Mr. Beck. Today we're going to be talking about two different sections. The first one is power series, and the second one is about geometric power series. Just as a quick recap as to where we've been, in Chapter 8, we've talked about just a bunch of different series and whether those series converged or diverged. With that, we had the nth test for divergence. We had geometric series that converge if the ratio is less than 1. We worked with some alternating series. We worked with ratio test, root test, just to name a few. Honestly, we've been doing quite a bit this chapter. So when it comes to power series, first thing we want to do is identify what a power series is. So a power series is an infinite series of the form where we have the summation of some rule times x to the nth. Now, if you remember, as we talked about the Taylor series, I tried to generalize and put it in the summation form, where for the Taylor and Maclaurin series, what we did was we took partial sums, but then I ended up writing the rule just to say, hey, we're going to be working with these. So this one kind of models what happens if we have the Maclaurin series because our center is at x equals 0. So we can tell that because this is x minus 0 to the nth power. The bottom one is more of a Taylor series in general because we do have a center. So this is the center at x equals c. So with that said, our first set of directions are see if we could find the center of convergence for each series. So to do that, what I'm looking at specifically is this is x to the n, therefore our center has to be 0. This is x plus 1 to the n, which is x minus negative 1 to the nth power, which is why our center is negative 1. This one is x minus 1 to the nth power, so our center is 1. Very, very straightforward. Just we want to know where our center is because where the center is determines what the power series is going to look like. Going on a little further, a power series can be considered a function of x, where the domain of f is the set of all x for which the power series converges. So in short, this function is equivalent to the power series, but only where we have convergence. So our goal is to figure out, first of all, what the series is, and then second of all, where does it converge? I guess we're going to start more with where is it going to converge. So where it converges is one of three cases. First case is the series converges only at x equals c. All right, so what does that mean? Let's take a look at the cosine function that we worked with last time. So we have our cosine function, which does this. And we started approximating with a series. The way we started approximating the series was we created a function. In this case, it was a 0-degree function, or you could say linear function as well. We ended up building off of that to show convergence for a rather large area. But if we just had these two functions that we were comparing, they only converged at one spot, and that would be the point itself. So when that happens, that's what we call having a radius of convergence of 0. So the radius of convergence is 0 for that. We also have the series converges absolutely for all x, which means that their radius is infinite. Now, going along with this analogy further and further, what I ended up doing here was I ended up adding more and more terms, and pretty soon we saw where the function that we created ended up modeling the cosine function really, really well. So if it only converges at one point, the radius is 0. If it converges everywhere, the radius is infinite. Now, those are going to be the two easy cases that we work with, but that third case is going to be what happens if the radius converges for some real number n. So if it converges for some numbers but diverges for others, and a good example of that was the e to the negative x graph that we talked about last time. So that e to the negative x graph we modeled with polynomials. Let me change colors on this one. We modeled with polynomials, but then at some point it shot up. So we had convergence around a certain region. That's what we mean by radius convergence. How far away from our center, our radius, how far away from our center do we have convergence of the two functions? So when we took a look at that, one of the things I said is, well, it sort of looks like it converges up to here and up to here. But some people might say, hey, it converges that far. Somebody says, you know what, I prefer to be very, very exact. So when it comes to radius of convergence, we could look at it and it's really more of a personal judgment. Or is it? We don't want it to be a personal judgment. This is math. We have some absolutes. So what we do is we will use the ratio test to determine exactly what our radius of convergence is. So if you remember the ratio test, what we're doing is we are taking any series and we are modeling it sort of as a geometric series. So any next term over the previous term, we need to know what's happening there. So with the ratio test, we're going to say that geometric series has a ratio. We need it to be less than 1 to guarantee convergence. So, and a lot of our problems, what we're about to do is we are going to take the series that we have and we are going to use a ratio test to determine where we're going to have convergence. And remember, that ratio must be less than 1 for it to be true. So let's get on to it. So we take our series, which we have our rule 3 times x minus 2 to the nth power. So if we take the next term, which is the n plus 1 power, over that term, we set it less than 1. And the reason why we set it less than 1 is because we need that geometric ratio-ish to be less than 1. Simplified, I will get this expression. We just have x minus 2. So if I take the limit, notice there's no n to plug in. So I end up with this expression, and that's our goal. We need to have the absolute value of x minus c less than r, which is what I have written up there. So that means our c is 2, so our center of convergence is 2. You can see that up here as well. Our radius ends up being 1, so our radius is 1. For the next problem, a little bit more complicated of a function, which is totally okay. So a little more complicated of a function, I'm still going to use the ratio test. Now, because this is fractional, what we end up doing a lot is let's just skip that first step of taking the term divided by the previous term, or next term divided by the previous term. And we're just going to go ahead and turn that division into multiplication. So we have the next term divided by, aka times the reciprocal of the previous term. And then we do some reducing. I see the exponent 2x plus 3 and the exponent 2x plus, or 2n plus 1. So what that means is we just have 2n plus 3 minus 2n plus 1, which is just x squared. We have negative 1 to the n plus 1, negative 1 to the n, which simplifies to just negative 1. So a lot of exponent rules are going to come into play here. Then, if you remember, 2n plus 3 equals, or factorial equals 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. It's kind of hard to see. So what ends up happening is the 2n plus 1 factorials cancel out or reduce out, and I still have this left in the denominator. Now, when I take my limit as n approaches infinity, I get 0. So if this limit ends up being 0, what ends up happening is this is always a true statement, so our radius of convergence is infinity. And just so you know, this is our sine function. So, and that sine function I showed you last time converges everywhere. We'll learn about that being the sine function a little bit later. Now, if we're going to find the interval of convergence, first thing we have to do is find that radius of convergence. And then once we find our radius, we're going to establish that convergence on the open interval from c minus r to c plus r. Okay, great. Now, what happens at the endpoints? At the endpoints, we're going to have to use a ratio test or a series of other tests to determine whether we have convergence or divergence at those endpoints. So we don't necessarily have to use a ratio test. I don't like that in my directions, but so be it. All right, first things first, let's find the interval of convergence. To do that, typically I want to say, what's my center? Because there's nothing being subtracted, my center equals 0. Now, if I use the ratio test, the next term divided by the previous term, simplified, and now take the limit as n approaches infinity. Wait a second, this is just like the one we did before, where 0 is always going to be less than 1. So our radius of convergence is infinity. Therefore, the interval of convergence is all real numbers. So that means this function is going to model the actual function always. On example 5, not quite as simple. So, and that's why it's going to take a lot of space. With that said, let's go ahead and identify one more time what's the center. Center is at c equals 0. Then we say, okay, to find our radius of convergence, take the ratio of the next term to the previous term, and then simplified. A lot of the exponent rules will cause a simplification. If you have any questions about that, please ask at any time. So then I take the limit and I have an n squared over an n squared. And if you remember from chapter 1, that limit just ends up being 1. So this expression is the absolute value of 4x is less than 1. which when we solve for x, the absolute value of x is less than 1/4. And remember, our center is at 0, and our radius then is 1/4. So our interval is going to be 0 plus or minus 1/4 to 0 plus 1/4. So that's going to be our general case. But now we have to determine what's going on at the endpoints. So at the endpoints, if I take negative 1/4 and I plug negative 1/4 into the function right here, I will get negative 1 to the n over n squared. Now we know that converges by the alternating series test. So what happens is at negative 1/4, I'm going to include a bracket there because that endpoint does have convergence. And then I'm going to go ahead and plug in 1/4. So if I plug in 1/4, I will get, and once again, I'm going to plug 1/4 in for x up here. I will get 1 to the n over n squared, which converges by p series. So that tells me that this endpoint of positive 1/4 has a bracket as well. Putting all of it together, our interval of convergence is from negative 1/4 to 1/4 inclusive. And that is my overall answer. All right, example number 6, same thing. Take the ratio of the next term to the previous term. Simplify it to get this expression. Please make sure you know how to simplify that. Pause if you need to work it out on your own. Then what ends up happening as n approaches infinity of this expression, we do get infinity. Infinity is never less than 1. Therefore, our radius of convergence is only at 0. So what that means is the only interval of convergence, I don't really like writing it this way, but our only interval of convergence is just at x equals 5. How did I know x equals 5? That was my center. I meant to say that earlier. Hopefully all of you are identifying what the center is. So on example number 7, let's do that right away. Center is 2. Now that I have my center is 2, then let's go ahead and find the radius of convergence. So the limit of the next term divided by the previous term. Simplified, I get this expression. And then I take my limits and I notice I have an n over an n plus 1, and that limit at infinity is 1. So I get the expression x minus 2 over 2, absolute value is less than 1, which gives me the absolute value of x minus 2 is less than 2. So that tells me if I set it up as the inequality, I know x has to be between 0 and 4. Okay, so my interval of convergence is from 0 to 4. Now the question is, what's happening at x equals 0 and what's happening at x equals 4? So at x equals 0, what I'm going to do is, once again, plug in 0 up for x in the original series, and I get this expression, which if you see, and I'm zooming in here, if you see, reduces to negative 1 over n. Now, I'm not sure why that got cut off on the page, but negative 1 over n, the sum of that is divergent, and it's divergent by saying the negative 1 over n. So that's a p-series divergence, so we have divergence. So what that tells me is at 0, I diverge. Therefore, I am going to have an open bracket at x equals 0. Then let's go ahead and figure out what's going on at x equals 4. At x equals 4, once again, I plug in 4 for the x value up here. 4 minus 2 is 2. So that gives me 2 to the n plus 1. And then simplified, I get negative 1 to the n plus 1 times 2 over n. So this is a alternating, and that's what that a is. This is alternating, so by the alternating series test, I have convergence at x equals 4. So I have divergence because negative 1 over n diverges. I have convergence for the second part because negative 1 to the n plus 1 times 2 over n does diverge, or converge, excuse me. Now, this goes into why did we care so much about conditional convergence and absolute convergence? So the conditional convergence allows us to have different, I don't want to say signs, to have open versus closed. So if it's conditional, one would be open, the other one closed. Versus if we take a look at the very first problem we had up here, both sides converged. So that's where we had the absolute convergence, where it didn't matter that it was alternating, we had convergence regardless. On to the next problem, very, very similar. Take the ratio of the next term to the previous term, and let's identify our center just for fun. c equals 3. So then we reduce, find the limit, which we have an n plus 1 over an n, so that limit is 1. Now we take that absolute value less than 1. So once again, we have to figure out our center is 3, our radius of convergence is 4, set up the inequality, and we don't need the absolute values anymore. So then our interval is going to be from -1 to 7. Now, where does it converge? Does it converge at both endpoints or just one? That's where we're going to show the work. So at x equals -1, I plug in -1 one more time. I'm going to plug -1 in for x up here. And I get this expression, which simplified turns into this. Now, this is modeling sort of a -1 to, or like an alternating 1 over n plus 1. So that gives me some convergence because of the alternating series test. I always like to just specify in my mind as I'm doing these, why does this happen? So that why does it happen forces you to make all of those connections, which really ties this entire chapter together. If I plug in 7 for x, I will get 4 to the n plus 1 over 4 to the n plus 1 and n plus 1. Simplifies to this. Remember, this does not diverge by p-series. This diverges by usually a limit comparison test to a p-series 1 over n. So therefore, we have divergence at x equals 7. We have convergence at x equals -1. Now, hopefully you're recognizing that a lot of times we're going to have one side converge and the other side diverge. So when that happens, the only reason for the convergence is because it's an alternating series. So wherever that -1 to, we have that -1 that's still left over when we plug in our x value, that's where we typically are going to have convergence, versus if we don't have the alternating aspect, we typically have divergence. Now, it's not always true, as we saw the first problem that we really did, but that's kind of like this is what I expect. Anyway, some properties of the power series. So what we could do with the power series, remember we said the function is equivalent to the series along the radius of convergence. So along the radius of convergence. I'm going to make sure I throw that in here. So along the radius of the convergence, these functions, we can treat them as identical. So since we treat them as identical, then f is differentiable on that interval. So to have it differentiable, what's nice about this as a power series, the variable is really x because we're saying f of x, or independent variable is x. So this is a power rule. So we're going to take the n, put it in front, and we'll say n minus 1. So n minus 1. Now, one of the things that I want to hit hard is our series. We're saying we're starting at n equals 0. And I will say this is going to be modeling more of a geometric series, and more to come about that. A geometric series, we will start at n equals 0 for that. Now, when we take the derivative, notice how it changes to n equals 1. So typically when we take the derivative, we're then going to say we're starting at not the initial term, we're going to start at the next term. So one of the reasons for that is in a series like this, then the first term is a constant. So when we take the derivative, that constant falls out. So our first derivative is really going to start from that first term on. And if we took the second derivative, typically, especially because this one's linear, so the second derivative would then start at n equals 2. So if we did f double prime of x, we would say the sum n equals 2 to infinity. Then it would be n minus 1 times an x minus c to the n minus 2. Now, we can kind of look at it this way. What happens if we plug in 2 here? We will get 2 minus 2, which is 0. Great. What happens if we plug in 1 here? 1 minus 1 is 0. So it's really kind of establishing what that term is. Now, if we would have tried to plug in n equals 0 to either here or here, we're going to start creating some issues. And those issues is then we'll have x minus c to the negative second power. That's going to honestly break the series. So one of the things you should expect is we are going to increase one value or one n term every time we take the derivative. Now, if it's differentiable, we could always look at it and say, can we integrate it as well? So we can integrate f of x as integrating the series. So as a power rule, we will take the next exponent divided by the previous, or divided by that new exponent. So when we do that, we get this overall expression. Now notice how I have a plus c here, and also notice that n still starting at 0. So we're not going to say n is going to start at -1, so we're not going to go backwards. What ends up happening is that plus c value kind of compensates for what would happen if we added another term to it. It usually is possible to say once we have our c, we can go ahead, try to combine it into the rule. Typically, it's not worth it, to be honest. So, and then here's just that expression right now, which if we take a look at the original one that we had, if we integrated that, you should be able to see that's what we get. The radius of convergence of the series obtained through differentiating or integrating is the same. And everybody, let's highlight that. In fact, let's do that in a different color just to emphasize what's going on. The radius of convergence, whether we integrate or differentiate, is the same. The same. I'm going to highlight the same. This means we're going to save ourselves a lot of work by not having to refine the radius of convergence over and over and over again. Okay, trying to save you guys some time here. Now, the big difference is the endpoints. Convergence at the endpoints may be different. So we're still going to have to check the endpoints like we just learned to do, but the radius ends up being the same regardless. So think about it this way. If the functions are identical or we are treating them as identical, if you have along that whole radius, if you can differentiate the function to begin with, you should be able to differentiate the series along that same interval. So example number 9, you see there's a lot of work involved in example number 9. So let's focus on the left side to begin with. And I'm going to go back to highlighting in green. So first thing I want to do is establish what is my radius of convergence. And of course, what's my center? My center is at c equals 5. So what's my radius of convergence? Ratio test, next term divided by the previous term. Simplified it to this expression after we found the limit. So we know that we're going between 0 and 10. Yes, we still need to establish what's going on at the endpoints. So when we plug in 0, we end up with not alternating. It's just the sum of a bunch of negative terms, and that diverges by p series. And so because it diverged, we have the open parentheses. At x equals 10, when we simplify, we end up with an alternating series, so we have convergence there. So we're going to converge at the endpoint of 10. Now let's go ahead and take the derivative. When we take the derivative, we're going to bring that n out in front and say that's n minus 1. Notice how I then change this to n equals 2, because we're going to start at the second term, not just the first term. So when we do that, the n's will reduce, and since those n's reduce, I have the simplified expression right here. So with that as my simplified expression, I need to establish what's going on at my endpoints. So at x equals 0, if we plug in 0 for x and simplify, it simplifies to the sum of a bunch of 1/5. Now, one of the things you got to be watchful for is this negative. What I did was I combined the negative from in front of the 5, and let me kind of write this on the side. I'm taking -1 to the n plus 1 times -1 to the n minus 1. If we add those exponents, we get -1 to the 2n, which is why I have that part of the expression. So now it's -1 to the 2n over 5, which is because -1 to the 2n is always going to be even. It simplifies to the 1 over 5, which diverges. Then at x equals 10, what happens? Let's go ahead and plug in x equals 10, and I will get that expression. Simplified gives me my alternating. So this alternating, but we have to be watchful for. This is not like the alternating series that we were looking at. This is not convergent, it's actually divergent. Why is it divergent? Because our terms are going to alternate between -1/5 and 1/5. So our sum is not going to be a consistent number. This is a non-decreasing function. Our sum is not going to be a consistent number. It's either going to be 0 or -1/5. So this diverges. So we could say by the alternating series test, but it's more of the nth term test is not actually 0. So our radius of convergence is 0 to 10, non-inclusive. For our second derivative, once again, we're going to bring our exponent out in front, subtract an exponent. then if you notice, I just kind of like jumped to the answer, because what ends up happening here is when we take the limit as n approaches infinity, then we're always going to have the numerator greater than the denominator. And because of that, we're always going to have divergence by the nth term test. So our interval is from 0 to 10. All right, let's analyze what just happened, and let's come up with a shorter approach. If you notice, we started off with the interval from 0 to 10 where we included 0, or we included 10 but not 0. If you notice, 0 was never included in either one of the derivatives. And so why is that important? Because if we can't take the derivative in essence of that endpoint to begin with, any derivatives that we take from there on, or if we don't really say that point exists, we can't take the derivative at that point anyway. So we're never going to have convergence if we started off with divergence and we're taking the derivative. Now, if we look at x equals 10, when we took our first derivative, we ended up seeing that we had some divergence there. Since we had divergence at x equals 10, we're never going to have convergence afterwards. So that's why we can really just jump, define the radius of convergence. The radius is going to be the same, and the moment we have convergence, we're taking the derivative, those endpoints are going to be the same as well. All right, differentiation done. So let's take our opportunity to do some integration. So when it comes to the integration rules are still going to apply. And what I mean by that is we're going to raise the exponent and divide by the new exponent. And then we take the limit as x approaches 0, or sorry, as we take x equaling 0. And when we do that, I have this simplified expression. Now what happens is this ends up always being a positive value. So this is 5 over n squared ish. If we do a limit comparison test, that would be convergence. At x equals 10, we already know it converges at x equals 10. So kind of like the logic that I've shown before, since we already knew the convergence at x equals 10, we're never going to diverge after, and we're integrating, never going to diverge after we've already begun to converge at that endpoint. So if I took the second integral, then I would still have convergence at x equals 0 and x equals 10. So then we get to our AP problem. One of the things that a student mentioned in class was, I don't feel like any of these answers are correct. And I was like, well, what do you mean by that? And they said, well, we are differentiating. This one starts at n equals 1, and all of our answer choices were also n equals 1. So why is that true? And I was like, that's a very, very good question. First thing that I did want to point out is what happens when we take the derivative. The 2n minus 1 in the numerator is going to cancel out the 2n minus 1 in the denominator. So we end up with just this expression. A is the answer. Now, to answer the student's question, I looked at this and said, okay, let's write out the sum of all of our terms. So plus dot, dot, dot. So if we write out the sum of all of those terms, then what we can see is our first term is not actually a constant. Our first term is linear. So when we took the derivative of the first term was still important because that derivative was 1. So we are going to still start at n equals 1 in this case. Now we could show that if we look at the overall series and we plug in n equals 1, if we plug in n equals 2, n equals 3, we can see that we are going to end up creating the series that we see right here. So I'm confident that n equals 1 is an okay idea to start with here. So you don't want to just immediately jump and add 1 to the n value. You really should be checking everything out. But typically we can expect that we should have adding 1 to the n. All right, 8.8 is over. 8.9 talks about geometric power series. And this is one of my favorite lessons when it comes to series overall, because there's a lot of creativity built into what we're about to do. So if we take a look at f of x equals 1 over 1 minus x, notice how this actually resembles a over 1 minus r. So what we could do is we can establish, okay, that 1 is really our starting value and that x is our ratio. So if we could write that as a geometric sum. So the sum from n equals 0 to infinity of x to the n is equivalent to this function along a certain radius of convergence. And it happens that the radius of convergence for this series is 1. So what happens if I want to represent a different interval? What happens if I don't want to center this at x equals, excuse me, at x equals 0? So this one is centered at x equals 0. So if that's centered at x equals 0, what I could do is I could take any function and manipulate. What happens if I want to center it at x equals 1? I need to write the denominator so it's minus x minus 1. And then we compensate by figuring out what that value should be. So if that needs to add to the 2 minus x, and I have something minus x minus 1, that value needs to be 1. So then I could say my first term is 10, and then my ratio is x minus 1. So really, in essence, we are turning functions into geometric series, which in my opinion is very, very awesome. I never, before I took a calculus class, I never thought that that kind of idea was possible. It's fascinating. So let's take a look at our power series centered at a certain C value. So if I wanted to do that, I could center this at, if I tried to show what I did up at the top, I could say 1 minus the quantity x minus 5, but that gives me a center of C equals 5, not C equals 0 that I want. So another option that I could do is I could divide everything by 6. And in doing so, then my center remains at C equals 0. So I could write that as my first term is 2/6, which is 1/3. My ratio is x over 6. And so then I identify what is my interval of convergence. Since my center is 0, absolute value of that has to be less than 1. So I'm going to go from -6 to 6. Now, at this point, somebody usually asks, don't we need to test what's going on at the endpoints? And the beauty of it is, no, we don't. We don't have to test the endpoints because this is modeling a geometric series. So as a geometric series, the ratio must be less than 1. Ratio cannot equal 1. All right. What happens if I want to center it at C equals -2? So if we have C equals -2, then I need to be able to rewrite my denominator so that it's minus x plus 2. To do that, if it's minus the quantity x plus 2, I need to compensate and say, okay, that's a -x minus 2, so I need to have a positive 8 to compensate. So then I have 2/8. I'm dividing everything by 8. And then my first term is the 1/4. And this ratio is the x plus 2 over 8. So what's my interval of convergence? My center, remember, is at -2. Let me write that down. C equals -2. And then I go ahead and write that as the absolute value of x plus 2 over 8 is less than 1. Write it out as an inequality. So I then say from -10 to 6. What happens if we have a coefficient in front of that x? It makes it a little uglier. So my center, if I want it to be at 3, I need to write it out as -3 times x minus 3, which means this term needs to be -3x plus 9. And to compensate, subtracting a -3x plus 9 to make the 3x plus 2, that must be 11. Which then divide everything by 11. So that's my first term that I'm highlighting right there. And here's my ratio. So then define the interval of convergence, set the absolute value of the ratio less than 1, which if I multiply everything by 3/11 gives me this expression. So I'm just going to leave it that way. Probably shouldn't be lazy. We should probably say the interval of convergence is that 9/3 minus 11/3, so -2/3. And then 9/3 plus 11/3 is 20/3. So there's my true interval of convergence. All right, when it comes to operations with power series, the big thing that I want to highlight here is for a function, if I want to plug something other than just x into the function, I could really just write the series with that same thing plugged in. So I guess I should highlight there, same thing plugged in. Now the sum and difference, and this is the one that I'm really going to focus on right now, the sum and difference of those series. If I have a series that I want to break up into 2 or more terms, I can break it up as really 2 different series. And typically I do want to say something times x to the n. So we'll want to simplify our overall solution when and how we can. This will be highlighted more on example 3 than it is on example 2. So for example 2, just a little bit more complex. Since it's a little bit more complex, what's happening is it's not just going to be a straight linear denominator. So I still manipulate my function so it looks like a geometric series, or the sum of a geometric series. Divide by 2. once I divide by 2, then my first term is 2, and then my ratio is negative x squared over 2. I can write it this way if I wish, and that's typically, you want to. But anyway, the absolute value of that ratio has to be less than 1, which means I don't even have to worry about negative numbers. But then to solve that part of the inequality, the absolute value of x has to be less than 2. If I take the square root of both parts, I will get a new absolute value that comes out of it, which is kind of fun. It gives me an interval from negative square root of 2 to the positive square root of 2. For part B, I have x squared plus 2x, so now I have another term added. Hey, let's complete the square. If we complete the square, then I get minus 1 additionally, which I can write this in its completed square form. But it's a lot easier for me to just factor in negative out of the denominator to get into that 1 minus form. So my first term is going to be negative 6 if I have it from that form. My ratio is x plus 1 squared. And so then we've been doing all of this time. Sorry about that. I hit a random button on my iPad. Absolute value has to be less than 1, which then says x plus 1 has to be between negative 1 and 1. So my interval is from negative 2 to 0. My directions from the next part says, hey, let's use partial fractions. And a lot of question is, why would I use partial fractions? Well, the reason why I'd use partial fractions is because my numerator now has an x value in it. So if I use partial fractions, I did sort of a shortcut on this one. We know that it needs to be a over x minus 1, b over x plus 1. And if we work through the partial fractions, we'll find that both coefficients end up being 1/2, which then rewriting both of these series, I could say the first one has an initial value of 1/2 and a ratio of negative x. Our second one has an initial value of 1/2 and a ratio of x, which I'm going to go ahead and leave it that way. We can write this into a much more simplified function if and how we can. I'm not going to talk about that right now just because it's not quite as intuitive to do that. I'm very happy to kind of go through some of that with you. Basically, we have to write this as a piecewise function, and then typically we rewrite the series so that it's a straightforward going from n equals 0 to n equals 1 to n equals 2. This one, if you remember what we did with some of the previous series, what happens if one of our terms is a number and then the next term is 0, the next term is a number, and the next term is 0. Typically, we want to rewrite our functions. But anyway, when we look for the radius of convergence, we really have to compare both radii together. Now, it turns out both of these just go from the interval negative 1 to 1. However, if we look at part B, once more, break it up into 2 separate terms. And I skipped over the work on the partial fractions on that. Hopefully, you guys don't mind too much about that. When I did that, I will get these expressions rewritten in its geometric series form. So our first term times the ratio, first term times the ratio to the end. Now, this is where we're going to compare both ratios. First ratio has a radius from negative 1/3 to 1/3. Second ratio has a radius from negative 2 to 2. Now, it has to be true for both of these, so we're going to take the more restrictive version, which is the negative 1/3 to 1/3. Moving right along. What happens if I want to turn a series like, or turn a function like the natural log of x into a series? Natural log of x, there's no way I could rewrite the natural log of x as something over 1 minus something. So let's take a look at the derivative. So if we take the derivative of the natural log of x, we get 1 over x, and this is where we can turn this expression. Now it's a little bit more algebraic. We can turn it into 1 over 1 minus the quantity negative x plus 1. Now, for the record, that's not the most intuitive thing, but that's okay. So then my first term is a positive 1. And my ratio is, that positive 1 really was right there. Ratio is the negative of x minus 1, which if I rewrite it looks like this. But remember, this is f prime. So if this is f prime, and my goal is to find f, well, f is going to be the integral. So we will integrate both sides. And when we take the integral of that series, so the integral dx, then I end up with this series right here. And then we have a plus c. Don't forget, when we integrate, we always have to add a constant onto that. What is that constant? How do we find that constant? Well, let's take the what our function is. F of x is natural log of x. Everybody, what is f of 1? 0. So we're going to say 0 equals that with the x value of 1 plugged in, which then if we have 1 minus 1, that's going to be the sum of a bunch of zeros. The sum of a bunch of 0 is indeed 0 itself. Therefore, c ends up equaling 0. So there is the function. Now, one of the things that we could do with this function is we could say, all right, what happens if I want to start that at n equals 1 instead of n equals 0? What that means is I can subtract 1 from each one of these exponents. And that's looks a little familiar. This is our natural log function that we did when it came to Taylor series. So what's really, really cool is we could use, or really we can connect all the information that we've learned, that this is a geometric series, but it's also the integral of this is a Taylor series, but it's also the integral of a geometric series. Awesome. I love how it all connects. But anyway, last problem, and I know you guys are sad this is the last problem. Once again, I took the derivative. That derivative is 2 over 1 plus 4x squared. Just remember it's the derivative of what's inside over 1 plus what's inside squared. Then you see I rewrote it. So my first term is 2, and then my ratio is the negative 4x squared. Negative 4x squared to the nth power, I rewrote as negative 1 to the n, 2 to the 2n, next to the 2n, which is what I've established right here. And then if I take the integral, it would be 2 to the 2n plus 1 over 2n plus 1. We still have our alternating, of course. New exponent is x to the 2n plus 1. And plus c, don't forget that plus c. And we do know that the arctangent of 0 is indeed 0. So if I plug in 0 for x, I will get the sum of a bunch of things times 0 plus c. So c ends up equaling 0. So our arctangent is simply that expression. One of the things we have to watch out for, and I know I mentioned it, but a lot of students forget, remember this series does not really represent the arctangent 2x everywhere. It only represents the arctangent 2x along the radius of convergence. And if we were to find the radius of convergence, which our directions do not ask us to, we will have to go and do all the things that we did earlier today. And it shows that the interval is going to be from negative 1/2 non-inclusive to positive 1/2 inclusive. Hopefully you guys learned a lot today. I had a lot of fun explaining it to you. I hope and take care.